The CPU is the heart of a computer, and in this video we'll figure out exactly how they work, building them up from the very basics all the way to a functioning CPU. But not just any CPU, we'll talk about the RISC-V CPU, which uses an open source instruction set which is growing more and more popular. Before we start designing the CPU, you need to know how instructions are turned into binary numbers, which is the language of our CPU. If you don't know about the RISC-V instruction set yet, you should watch our previous video on it. An instruction will be converted into a 32-bit number, but to figure out exactly which of these 32 bits will contain what information, we need to look at the specific type of the instruction we're looking at. In an instruction like add-I, we have an input register, a 12-bit immediate, and an output register. We have 32 registers, so they can be represented using 5 bits. Which means that of these 32 bits of machine code, exactly 5 will be used to tell the CPU which input register to use, 5 will be used to tell the CPU which output register to use, and 12 will be used to indicate what the immediate is. The other 10 can be used to tell the CPU that this instruction is add-I and not some other instruction. Compare this to an instruction like add, which takes in 2 input registers and 1 output register. In this case, 15 bits of machine code will be used to tell the CPU which registers to use, and the other 17 to tell the CPU that this is the add instruction. What we've seen is that depending on whether we use an immediate or not, and depending how many registers we use, our machine code has a different meaning. From this, we can break up all of the RISC-V instructions into 6 different types. R-type instructions if we take in 2 input registers and 1 output register. I-type instructions if we use an immediate. S-type instructions if we store data into memory. B-type instructions for branching. And finally U-type instructions and J-type instructions, which are load upper immediate and jump and link instruction. In each format, you can see that the 7 least significant bits are used to encode the operation code or opcode. These tell you the type of instruction you're looking at. For example, if the opcode is 51, you're looking at an R-type instruction. If the opcode is 99, you're looking at a B-type instruction. If it's 23 or 55, you're looking at the U-type instruction, and so on. In some cases, such as when the opcode is 111, the CPU knows exactly what instruction you're referring to, since the jump and link instruction is the only instruction with that opcode. In most cases, however, just giving the opcode is not enough information to figure out what instruction is being referred to, which is why there's a func3 field and sometimes a func7 field. These are just some extra numbers to specify which instruction you mean. You might also realize that we actually have a ton of different opcodes and func3 fields which aren't used. These can be used by extensions to add new instructions and new functionality. Let's try to convert some assembly into machine code by hand. Let's say we have these 7 lines of assembly. I'll admit it doesn't do anything useful, but it's a good exercise in understanding machine code. The first instruction we convert into machine code is this line here. We know that the XOR is an R-type instruction. So from our table, we can read off that the opcode is 51. The func3 field is 4 and the func7 field is 0. We'll just fill in those numbers into the R-type format. As for our registers, T0 is register X5, so fill in 5 in that spot. S5 and A0 are X21 and X10 respectively, so fill that in to finish our first line of machine code. Let's move on to the second line. OR immediate is an I-type instruction, of which you can read off the opcode and func3 value in this table. Registers T2 and T6 are X7 and X31 respectively, so we can fill those in as well. The immediate is the number -501, which you need to convert to binary using 12-bit 2's complement to find our line of machine code. For a third line, branch if greater than or equal has opcode 99 and func3 5. Registers A0 and A1 are X10 and X11, so we'll fill all of that in as well. If we look at a format, you can see something strange. Format expects an immediate in the remaining slots, but B-type instructions don't use immediates, they use labels. If you remember from our previous video, the way branch instructions work is by adding a number to our program counter. In this case, by jumping to line 7, we jump 3 lines, which will mean an increase of 12 for our PC, since the PC always increases in multiples of 4. However, of these 3 lines, 2 are white lines, so we only need to increase our PC by 4, which is the immediate that is expected in this format. It gets even more confusing, because although we only have 12 spots left for machine code, the immediate is actually 13 bits wide. This is because our immediate is always even. Being even, the last bit is always a 0 in binary, so we don't even need to encode that. So, to properly finish our machine code, we put here immediate bit 11, then bits 1 to 4, then bits 5 to 10, and finish it off with bit 12. Let's go on to the last line of code. The opcode for JAL is 111, and the 0 register is X0, so you can plug those in. Then we have 20 bits left for our immediate, but as with B-type instructions, they are actually 21 bits wide, since the last bit is always a 0. What is our immediate in this case? We're going up to line 2, which is going up 5 lines of code, meaning an immediate of minus 20. 2 of these lines can be ignored though, so the immediate is actually minus 12. Turn minus 12 into a 21-bit 2's complement number and fill it in. The format for the position of the immediate are once again a bit weird. Start off with bit 12 to 19, then bit 11, then bit 1 to 10, and finally bit 20. Here you can see the full machine code for our instructions. Of course, in real life, this process would have been done by an assembler, but doing this by hand helps us with understanding what each part of the machine code represents. Let's now actually start designing the CPU. We'll do so using a digital circuit simulator called Logisim Evolution, because it's free and really easy to use. In the top link in the description, you can find the GitHub page for the program. If you successfully installed and opened the program, you see a window that looks like this. I won't go too in depth into how everything works, but here are the basics. Here you can see the canvas in which we're going to build our circuits. By holding down the middle mouse button, you can move around, and by holding Ctrl and then scrolling, you can zoom in and out. In the Explorer pane, you can see a bunch of folders holding components that you can drag into our canvas. We select an object, and you see the attribute table containing properties for that component. You can edit some of these properties for components. Up here, you can see the toolbar. For our purposes, the most important buttons here are the poke tool, which is hand, the selection tool, which is cursor, and the pin tool, which is these two buttons. The selection tool is what we've been using the whole time, which allows to move and change certain components. The poke tool allows to interact with input devices. For example, let's add a dip switch from the input-output folder and add some LEDs. If we change from the selection tool to the poke tool, we'll change the state of these dip switches to turn the LEDs on or off. The pin tool is useful if you want to create sub-circuits inside our circuit. To create a sub-circuit, take a look at the Explorer pane and click on this plus. Let's give our sub-circuit a name such as sub-circuit and click on OK. It might seem like nothing has changed, but as this magnifying glass indicates, we are now inside of our sub-circuit. If we create some circuit in here, let's say 2 inputs for our pin tool and 1 output, which will be connected via an AND gate, we can go back to our main circuit by double-clicking on it. If we now drag our sub-circuit into the canvas, we can abstract a device that takes in 2 inputs, just as we had 2 input pins, and has 1 output. We can even test out to see that it works just like an AND gate. You might be confused about which pin corresponds to which input though. To fix this, let's go back to our sub-circuit and using the selection tool, double-click on our pin to give it a name. Let's go with A. Let's call the other 2 pins B and C. If you go back to our main circuit, we can see that these changes are added to the sub-circuit module. That was it for the quick explanation of the basics of Logisim Evolution. But if you're ever confused, you click this Help tab right here, and either click the tutorial, the user's guide or the library reference for more information. And feel free to just play around with Logisim Evolution. You can do a lot of fun stuff in this simulator with all the tools available. Let's now finally start designing the CPU. If you've watched our last video, you know that the CPU contains the register file, the memory, and a program counter that goes over the instructions stored in our memory. Of course, this is still going to be the case in our circuit, but to simplify the CPU, we're going to make a single cycle processor, which means we'll break up our memory into 2 parts. One for the instructions which our PC is going over, and the other one for our variables. This will result in 4 components for our CPU: the PC, the instruction memory, the register file, and the data memory. Each of these four components can be created as subcircuits, as was just explained. Let's start with the instruction memory. Since we only wanted to store instructions, we can create a ROM component, which you can find in a memory folder in our Explorer pane. A data word is 4 bytes wide, which is 32 bits. By default, the ROM has words which are 8 bits wide, but we can change that by editing the data bit width property. Another property we have to edit is the address bit width property. To get a full 4 GB of different addresses, we have to set it to 32. Unfortunately, the highest value Logic Evolution will allow us to go is 16. So let's just add 2 and use the first one if the PC tries to read an address below to the 16th, and use the second one if it's above that. If you remember from one of our previous videos, you know this can be done by subtracting the numbers and checking if the most significant bit is a 1. But in Logic, we fortunately have a comparator component, which abstracts the logic away for us. Let's add our input and output pins, which will be 32 bits wide. Now we need to compare the input pin to a constant value of 0x0001, 0000. If our input is less than this constant value, we use the least significant half for input. Otherwise, we use the most significant half for input. We can split our input into these two halves using the splitter. To choose one of them, we use a multiplexer. Where the select bit is not the less than sign. So right now, with an input of 0, we choose the least significant part, and with an input of all 1s, we choose the most significant part. For the output, we use the exact same logic. We can reuse the signal from a NOT gate and put it into a new multiplexer, choosing between the output of the first ROM and of our second ROM. We can name our input A for address and our output RD for read data. We can make our circuit look a lot nicer if we add these components called tunnels. If two tunnels have the same name, then it's basically as if they were connected by a wire. By using these tunnels, we can organize our circuit and make it look a bit better. Let's now go on to make the next element, the register file. Once again, we can make a new subcircuit. As you remember, the register file consists of 32 registers, each of which are 32 bits wide. We can copy-paste the register 32 times. It's also quicker if you first connect a clock to one before you start copy-pasting. Since the first one is always a 0, we can take a constant value from the library and connect it to the reset value. We have inputs A1 and A2, which allows us to choose the correct output based on the register we want. To choose this output, we can use the mux again. After a while of connecting wires, you should have something that looks like this, where every wire is connected to the mux. We could create an output RD1. Now add in a second mux for the A2 input and the RD2 output. Now we can read the values stored in a register file by properly choosing the values for A1 and A2. We still need to be able to write to them. We can do this with a combination of 3 inputs, the write enable 3, the write data 3 and the address 3 inputs. A3 tells the address of the register we want to write to, so if it's 0, it's this one, if it's 1, it's this one, and so on, similar to how A1 and A2 work. The WE3 input tells us whether we want to write, because we don't always want to write to the register file. And finally, WD3 is the actual data we want to write to a register file. For our A3 input, we want to split up this wire into 32 wires. Similar to how we chose 1 out of 32 wires with a mux, we now want to do the opposite, where we use address to get 32 wires back. The component that does this is called a decoder, which you can find in the library. After a while, we have every component connected. For the decoder, you can see we have 2 inputs. One is the actual address we need, so A3, and one is an enable for the decoder, which corresponds to our WE3 input. The final thing we need to connect is our WD3 input. This is going to be the same for all registers, because we're only writing to one at a time, so we can connect all their inputs together like this. Also note how we don't need to connect it to the 0 register. If you connect this final wire to our WD3 input, we are done with our register file. Let's build our last element, the data memory element. Like our instruction memory, it's a simple memory element, but this time it is extra special since we can write to it as well. I'm just going to copy and paste the same circuit from our instruction memory, but replace a ROM component with a RAM component. I'll add a write data input, or WD, and a write enable input, or WE, to control when to write and when to read. Both of these inputs should be connected with both RAMs, so they can change at the same time. Then we also have our clock input and our output enable input, which we have to connect. The clock input is simply a clock input we can create. For the output enable input, we can just set it to 1, since we always want to be able to read from a memory. With everything connected, we are done with our instruction memory. You might be wondering why I didn't add an element for our PC. That is because for our purposes here, it's probably easier if we just keep it as a 32-bit register. So with these 4 elements, the PC, the instruction memory, the register file, and the data memory, we should be able to create a CPU. Let's create an example program where we run this line of code. It's a simple R-type instruction and has the following machine code representation. We can go into our instruction memory by double-clicking on it with the hand tool, and then enter in the value by right-clicking into our ROM element. Let's go to our main circuit again and connect the PC to our instruction memory. If we add in these components called probes from the wiring folder, it makes it easier for us to see what's going on. We can see the output of the instruction memory indeed contains our line of code. Let's now split up this wire. We know that R-type instructions contain 6 parts: the OP, the output address, the func3 field, 2 input addresses, and the func7 field. Let's use a wire splitter to split our machine code into these 6 segments. Let's, for now, not worry about the func3, func7, and OP field, but instead just connect the input addresses and the output address. Since we want to add our registers together, we should go to the output of our register file and put an adder here, which luckily comes as a pre-built component in Logisim. Although this is correct, what we actually want to do to make sure we can handle all R-type instructions is create what is called an ALU, or an arithmetic and logic unit. The ALU is a component that contains a whole bunch of operations, such as adding, subtracting, XORing, shifting, etc. By using an external input signal called ALU control, we can choose which of these operations we want to perform. Let's create a subcircuit called ALU. This ALU will have 2 inputs, source A and source B. We'll still add them together, but now we also add other operations, such as subtracting, ANDing, and more. I'll not worry too much about making this an efficient simulation, because this is just for educational purposes. For the shifters, also throw away the last 27 bits of B and only keep the first 5. Because the shifter just takes in 5 bits for the second input. Now we have 10 outputs, which you need to choose one output from. This can of course be done by a mux as before. For the set less than and set less than unsigned, we get an output that's only 1 bit wide. What we need to do is called sign extend, which is turning this 1 bit into 32 bits. This can easily be done with a bit extender component. Once we've got everything connected, the output of our mux is then a real output. Let's call it ALU result. We still need to create a select input for our mux. Let's call this ALU control and make it 4 bits. If we go back to our main circuit, we can add in our ALU. For now, let's not worry about the ALU control input. Our ALU result output here should not do anything with our data memory, but instead be connected to the WD3 input of our register file. We also need to connect the WE3 input, but for now, let's not worry about it and just call it a rec write signal for register write. With all of the circuitry we've just created, we can actually run our machine code. Although right now it wouldn't do much useful, because the registers we're adding together contain the value 0. If you remember from our previous video, we choose add I to set the value of a register to a number. So let's add those I type instructions now. For an I type instruction like this one, we can again put it into our instruction memory as before. For I type instructions, the instruction format is different from R type instructions. Most things stay the same, but we have to combine our last 12 bits together to get our immediate. For all of these I type instructions, we really don't have to change much in our circuit. Our immediate just acts as the value in our second register. All we have to do really is connect the immediate to the source B input of our ALU. We can add in a mux to choose between RD2 and the immediate based on an ALU sourced input, which we'll worry about later. Since our immediate is 12 bits and our RD2 is 32 bits, we need to sign extend our immediate. Make sure for the extension type you put sign, so that if your immediate is negative, it stays negative when sign extended. We haven't used our data memory yet, so let's now implement the load word instruction. It's still an I type instruction, so we don't have to change anything about the instruction format. In the load word instruction, we add the immediate to the first register, so our ALU here is correct. The only thing we have to change is that now, instead of putting ALU result directly into our WD3 input of a register file, we should put ALU result into the address input of our data memory. The output of our data memory can then in turn be connected to our WD3 input. Luckily, this is really easy to implement. We just need to add a mux here to choose between our two outputs, using a result source signal, which we'll worry about later. The data memory isn't really useful at the moment because we haven't stored anything in it. Let's implement the store word instruction to store data into our memory. Since it's an S-type instruction, we need to change our instruction format again. Our wiring here is already pretty messy. Now we're going to make it even messier by introducing new formats. To make all of this a bit neater, let's create two new components. One which we'll just call immediate, and another which we'll call register format. The register format will give the right func3, func7 and register fields. The immediate will pick up the right bits from our machine code to get the correct immediate. Since the first 7 bits are always our opcode, I'll just ignore them and only focus on the last 25 bits. The register format is simple. Break up the machine code input into 5 different wires, each of which corresponds to an output we expect. The first 5 bits to the RD output, the next 3 to the func7 output, the next 5 to RS1, then RS2, and finally the remaining 7 bits are func7. The immediate is a bit more annoying. If you have an I-type instruction, we need to take the last 12 bits of our immediate. For S-type, we take the first 5 and then the last 7. For B-type, we need to change the order a bit. If you remember from a moment ago, we first have a 0, then bits 1 to 4, then 18 to 23, then bits 0 and 24. Let's split up our immediate into 4 wires and then recombine them back in the right order. Let's also put a constant 0 here, since the first bit is always a 0. U-types are just the last 20 bits, and for J-type instructions, we have to do the same thing as for B-type instructions, but now in a different order. Specifically, we ignore the first 5 bits, then combine the next 8, 1, 10 and 1 bits. Recombine them together with a constant 0, and we get our J-type. Let's sign extend all of these to 32 bits and add some labels to make it clear what each signal corresponds to. Then use a mux to choose the correct signal. We can use the select signal, immediate source, to choose the type of instruction we want. Let's call the output immediate and go back to our main circuit. Let's replace our current circuitry with new components we just made. as well as add some tunnels for signals we'll handle later. Let's continue where we left off with the store word instruction. We add our immediate and our RD1 together in the ALU. This will then form the address in our memory which we want to write to. So far, everything is correct already. We just need to connect signals to our WE and our WD inputs. Let's connect our WE input to a memory write tunnel, which we'll handle later. As for the WD input, this is of course just a second register, or in other words, the RD2 output of a register file. We've almost handled every type of instruction. Let's now handle B-type instructions with a branch if equal. We take in two input registers, and if they're equal, we add the immediate to our PC. We can compare whether the two registers are equal using our ALU and subtracting both numbers. If the result is 0, they must be equal. This is really easy to do if we add flags to our ALU. Flags are extra outputs that give us more information about the result we just got. For example, you can have a flag to check whether the output is negative, overflows, or for what the carry is. But we are interested in checking whether the result is 0, so let's add a 0 flag. For this, let's add a comparator with the number 0. It's not the most efficient solution, but it gets the job done. Now we need to add our PC to the immediate, but we already used the ALU, so let's put in a new adder. The output should be the new value of our PC. Of course, we shouldn't always do this. In some cases, we should add 4 instead to go to the next address of our instruction memory. Let's set a mux in front of our PC to choose between either the normal PC plus 4 or this new PC plus the immediate. We haven't implemented the PC plus 4 logic yet, so let's do that by putting an adder and a constant 4 here. For the select signal of our mux, we can create a PC source input, which we'll handle later. Before we finish up the CPU, let's look at the J-type instruction, the only one of which is the jump and link instruction. It adds 4 to the PC, and instead of setting the PC to that value, it writes that value to a register. So we need to increase our result source so the PC plus 4 can also be a result. What it also does is set the PC to the PC plus the immediate, but we already have the hardware for that. The only thing that's now missing for the CPU to actually run RISC-V code is a control unit. The control unit is what is going to set the values for all of the signals which I've ignored so far. It's going to take in the OP, phone 7, phone 3 and the 0 flag, and it's going to spit out the OP source, result source, memory write, ALU control, ALU source, immediate source and register write. If you remember from earlier in this video, the reason we even have an opcode is so we can tell the type of instruction we have. An opcode of 3 means an I-type instruction, an opcode of 51 means an R-type instruction, and so on. Let's create an instruction decoder inside of this control unit just to check what type of instruction we're dealing with. It will take in as input the opcode, and we can simply compare every relevant value to it to figure out its type. So compare to 3, 19, 23, 35, etc. from our instruction table. Once again, this is not very efficient, but it gets the job done for a simple educational CPU. Let's make all of these groups outputs for our instruction decoder and go back to our control unit. By having broken up all instructions, it's much easier to figure out how all the outputs should be connected. For example, the memory write output should be 1 when we're storing something, if you remember correctly. Storing corresponds to S-type instructions, so we're connected to the S-type. ALU source should be 1 if we're using the immediate in our ALU, which is when we're using I-type or U-type instructions, so we can OR those together. We need register write to be 1 for all types other than S and B, so we can OR all of those together. PC source needs to be 1 for the jump and link register instruction, J-type instructions and B-type instructions, but then only if the 0 flag is true, so I can put an AND gate here as well. Result source should be 0 if we're using the ALU, 1 if we're dealing with instructions where you load something from memory, and 2 if we're dealing with a jump and link register instruction or with a J-type instruction. You might try to put this in the same format as before with OR gates, but now we also need a new component called an encoder. In this case, what it does is it takes in 4 inputs, If the first input is a 1, the result will be a 0. If the second input is a 1, the result will be a 1. If the third input is a 1, the result will be a 2, and so on. The output tells you the address of the input that is 1, which in this case is exactly what we need. If there's nothing connected, we can just put a 0. The final two outputs we still need to address are the hardest. For the ALU control, we can see that for R-type instructions, we're only interested in the func3 input and the 6th bit of the func7 input. If we go up to the Window tab and then click Combinational Analysis, we can create a truth table for the circuitry we need. If we plug in the correct instructions in the order we have them in our ALU component, we can quickly finish this table. If you just click Build Circuit, we have the circuit we wanted. That's only for R-type instructions and I-type instructions that use different ALU operations. For S-type and I-type instructions that load data, we need to keep it 0 for adding. And for the branch of equal instruction, we need it to be 1 for subtracting. We can make another, simpler truth table for deciding which to use. If you aren't using an R-type instruction, nor a B-type instruction, we can add, which means an ALU control of 0. If it's an R-type instruction and not a B-type instruction, we can use the output of our previous combinational circuit. If it's a B-type instruction and not an R-type instruction, we can set it to 1. The case of both an R-type instruction and a B-type instruction is never happening, so we don't need to worry about it. This logic we just created can be implemented using a multiplexer. For our select signal, we need to combine the R-type and the B-type instructions into a single wire. Plug in the right constants and logic for our inputs and you get our ALU control signal. Last but not least, we have the immediate source signal. This signal was used to choose the correct type of instruction we were dealing with. This is close to what we've already done with the opcode, but now we just need to group all similar type of instructions together using OR gates. Then just use an encoder to turn them into a single number, and we're done with our control unit. We don't need to connect the R-type signal because I don't use immediates. To finish our CPU, we go back to our main circuit and add in the control unit with all the proper connections. Add in the clocks and the rest of the circuit, and for the PC, we can set the write enable to 1. Let's now test out our CPU. Let's say we have this code, which tests out all of the instructions we implemented, such as load word, store word, add I, sub, branch of equal, and jump and link. Our code consists of 3 parts. First, we set S0 to 600. Then we implement a loop where we subtract 9 from S0, and we go over this loop 10 times. We use the set less than instruction where T3 becomes 1 if T0 is 9. In which case the branch of equal statement is no longer true and we exit the loop. In the second part, we store the value of S0 in our memory at address 0. We then set S0 to 0 by subtracting it from itself. If S0 was stored correctly in our memory, we can retrieve it with a load word, in which case we will get our S0 of 510 back. After that, we use jump and link to go to the end of our code, but if this jump and link doesn't work, we set S0 to 5. After running our code, a value of 510 would mean that every step was successful, but a value of anything else would mean failure. If we put this code into an assembler, you can find the following machine code. If we put this into our instruction memory in steps of 4, then run our code. If we go into our register file, we need to find the value of 510 in register S0. Of course, there are still many instructions I didn't handle, which I'll let you tackle on your own. If you want to learn about more complicated CPUs, such as multi-cycle processors, which, in contrast to our single-cycle processor, uses multiple cycles to handle a single instruction, or maybe learn how to implement these CPUs in hardware description languages, please let us know in the comments.